Okay, so now we're ready to look at solid spheres and figure out the force that a solid sphere will exert on an object that is inside and outside the sphere. Okay, so let's first do the outside case. So we'll take a solid sphere, we'll take a point of mass m, let the mass of the solid sphere be capital M, let the radius of the sphere be r, okay, and let the distance be some lowercase r. And we're going to figure out the force that the solid sphere exerts on this mass m. Now this problem is very easy once we know what a shell does to the mass. Okay, so what we'll do is we'll take the sphere and we'll break it up into infinitesimal shells. Okay, lots of shells, and the force due to the shell we already know. Okay, let's say that the mass of the shell is dm, and we know that the force due to the shell, so we'll just call it df shell, is going to be equal to g times dm times m over r square. Okay, we already know this from the previous two derivations. Now to find the total force, okay, we'll take the f and we'll simply integrate the force due to the shell, and so it will be equal to g times m over r square, and we'll integrate dm. And since the mass of we're simply integrating the mass over all the shells, so what we end up getting is the relation gmm over r square. Okay, so again a simple expression for the case that is outside. Now to the inside case, you have to be a little more careful. Okay, so now if I have a solid sphere of some radius r, and let's take a point and let's put this at a distance r, so where r is less than capital R, and we want to find the force. Okay, so the one thing we'll do, we will draw a sphere passing through this point passing through the point where the mass is inside the sphere. Okay, the radius of this inner sphere, the blue sphere, is going to be equal to lowercase r, which is less than capital R. Now what we know is that we can break this into two parts. We can break it into the shell, okay, and we already know that the force of the shell on this mass is simply 0. Okay, so the only thing we need to know is we need to figure out the mass contained within the sphere, and we can find the force due to that inner sphere. So let's write this down. The total force F is equal to force due to the inner sphere plus the force due to the shell. We already know that this force is 0 because the shell does not exert any force on any particle that is inside the shell. So this is 0. So all we need to know is figure out the force due to the inner sphere, and we know that force is simply, once again, the capital G times mass of the inner sphere. So it's capital G times mass, just call it inner, times m over little r square. So the problem becomes finding what the mass is of the inner sphere. Now if it is a uniform shell, okay, if uniform, then the inner mass is basically equal to the density multiplied by the volume, which is 4 divided by 3 pi times lowercase r cube. So what we know is that the force is equal to g times lowercase m over r square times the density of this solid times its volume. And we simplify this, what we end up getting is gm rho, so let's put a pi, so pi gm, and we get 4 over 3 as well, okay, multiplied by r. So we know is that the force, okay, is dependent on the density of the solid, and it is, instead of being inversely proportional to the distance, it is actually now linearly dependent on the distance. Okay, we can graph this force, and when we graph the force, what we end up getting is F versus R, and let this be the radius R, and up to the radius R, this force is linear, and then after that it falls off as 1 over r square. Alright, so this is an important graph, something that you need to understand. And then the maximum force is what it feels at the surface, and if you were to find the values on the surface, you would end up getting the same from both the sides, and this value is nothing but gm m over r square. So this is the greatest value that you have. Now you can also ask, if the mass is given, the density rho can be found using the total mass divided by the total volume, which is 4 divided by 3 pi r cube. And if you plug it in here, okay, you'll see that the two forces at the surface of the sphere will basically be the same. So this is how to find the force inside and outside. Now later on, when we study simple harmonic motion, we'll see that the fact that the force is linear inside the sphere has some useful, important consequences, and one of which is that if you were to drop an object, okay, if there was a tunnel through the object, through the earth, for instance, if there was a tunnel that went right through the center, and if you dropped an object here, then this object would oscillate simple harmonically, okay, inside this tunnel. So, and that will be a consequence of the fact that this force is linear, and we'll talk about this when we study oscillations.